Hi everyone, I'm Anita Nantrajan doing my Masters in Arizona State University. As part of an assignment, we developed a device driver for ultrasonic sensors in Zephyr RTOS. And we thought of picking two topics or modules and talk about it. So we have chosen interrupt and I2C design well. So let's get started. Interrupt service routine, also called as the ISR, is a function that gets called whenever there is a hardware or a software interrupt. So this can be called asynchronously, which means if a current thread is executed in kernel and if an interrupt is received, it gets preempted and interrupt is given the top priority. Since ISR is always given top priority, we should make sure that it does not stall the other process in the kernel. So it has to perform its action as quickly as possible. If at all it has some work and that is to be performed by ISR and it is time consuming, it can delegate or offload its work to the helper thread. So what it does is, once the ISR is complete, it is going to context switch to this helper thread based on its priority. If the helper thread has a lower priority than other threads in the system, then those threads get executed and then the control comes to the helper thread. ISR can actually initiate the helper thread in two ways. One is to signal the helper thread directly and process its work, or it can actually send an alert signal to the existing work queue thread, which is going to do the action on behalf of ISR. Now we saw the general implementation or understanding of what ISR is. In terms of, now we're going to see the APIs and everything in terms of Zephyr. If we want to develop our own interrupt, how should we do it? First is the IRQ connect. This is going to register the IRQ with a number. Every IRQ or the interrupt gets associated with an IRQ number. So we have to, while registering, we have to specify what the IRQ number is going to be and what the priority of the interrupt is going to be and the function that's to be called whenever an interrupt is occurring, and what all arguments a function takes, if at all, if there is any, and the flags that is to be turned on. All these things gets registered. All these things should be specified when the IRQ is registered. Okay, and priority is required because whenever though interrupt receives the top priority, we do specify interrupt priority so that if one interrupt is occurring and if there is another interrupt that's happening, we should know, or the kernel should decide whether should the current interrupt be preempted or not, and that can be done based on the interrupt priority. So this is for registering the IRQ. Once the IRQ is registered, we need to enable or turn them on. So that can be done using IRQ enable. And if we want to check if the IRQ is really enabled, we have an API which will actually check whether the IRQ is enabled for this particular number or not. So if we have to register, we can first check whether there is an interrupt for this number. If not, then register or all this. So depending on our implementation, we can make use of these APIs. And if you want to, if at all our actions and everything is done, and if you want to disable an interrupt, that can be done by IRQ disable. Okay, apart from this, we also have a couple of more APIs for IRQ, which is the IRQ lock. It is going to lock the current thread or the current IRQ or whatever. Wherever this lock is applied, it is not going to allow any interrupt to preempt the current process. So that's what IRQ lock is. And this IRQ lock can be done recursively, meaning we can take multiple locks at a time. If there is an IRQ lock in a recursive fashion, then we should make sure that it gets unlocked in the reverse order. Also, if thread A is creating or is taking an IRQ lock, it means the thread A will not be preempted. But if thread A is creating or calling another thread B, then when the execution is when it is actually executing thread B, there can be an interrupt, but thread A will be uninterrupted. That is what the IRQ lock does. If thread B should also be locked from interrupt, then there should be an IRQ lock on thread B also. Okay, so which is nothing but the recursive lock of IRQ. And if we want to unlock it, we have to pass, as mentioned earlier, we have to do it in the reverse order to unlock it. Okay, now we saw about the general API like interrupt, and we saw about the APIs that is to be used in Zephyr. Suppose if you want to, we are going to use some GPIO pins and all those boards. Zephyr provides its API or its callback. Actually, it has a device driver for GPIO, and as part of that driver, we also have an ISR or the callbacks, which can be callback handler, which can be used for our purpose to define our own action on any of the pins. So first is whenever we have to, because the module or the device is connected to multiple board and multiple pin chips and everything. So first thing that we should do is we should actually detect which device we're going to work on. So that is done. So the device is picked using device get binding. It is going to retrieve the device for which the further subsequent action is to be performed. Or if you want to take an IRQ, first we need to find out which device we want to take. We want to get which device do we want to work on, and then suppose let's say we have picked up a chip, and then on this chip we will have multiple pins, GPIO pins. So once the device is obtained, we are going to configure the pin on the GPIO device. So that is done using pin configure, and it is set with some flag like debounce or active low, active high. All those configuration will be done here. Then once the pin is configured, we have to actually now initialize or register the IRQ. IRQ register is done using GPIO init callback, wherein the function or the IRQ function that we want to handle whenever there is an interrupt is given here, GPIO callback handler, and the pin, GPIO pin for which the interrupt is turned on. All these information is actually initialized here. GPIO callback is a structure that gets initialized with this information, that is the handler, and it also gets initialized with the pin information, on which pin should it be listening for which interrupt. All that information is actually passed in here. Once it actually initializes the GPIO pin with the required callback, it is going to add or enable. First is to add. Add means this GPIO callback is created. Now this callback should be associated with some device. So the device, GPIO device, is binded with the callback. So now after enabling or adding the callback to the GPIO device, we have to enable them. So that can be done using GPIO pin enable callback. So for this pin, the callback is turned on. Okay. Then you have the GPIO callback. This is the function that we have to execute. Like earlier we saw in GPIO init, whatever handler that we had, that is nothing. This is the user defined function. It can be any name. It's a user defined function which will take in the GPIO structure and the callback and the pin. And here in this function, we are going to define all the actions that we want to specify whenever there is an interrupt. Okay. So now these are the input parameters. If once the interrupt is done and everything is done, if you want to disable it and unregister it, we can go for these two APIs, that is pin disable and GPIO remove callback. Alright. Now we're going to move on to the next topic, I2C designware. I2C designware or I2C comes into picture whenever we want to communicate or transfer data between a slow device and a high device. So we know that, like all devices will not be having the same speed or something. So one may be slower than the other. So we don't want, the fast device to slow down. Instead, we want to have a buffer, and it is going to, as the high speed device is going to transfer or store all the data, the low speed can take as it can take. We just want to get the maximum benefit of both high and low speed. So that's when, we need some protocol or some means, some rules, so that the high speed device can communicate with low speed device and transfer the data or do its action. So that's when I2C comes into picture. So it allows, we have something called as the master and slave chip. So basically the high speed usually tends to be the master, which is going to initiate all the communication and generate the clock cycle and everything. And then a slave device is going to respond to what the master asks. And so it is, like before we said, it is to communicate with the microcontroller or any slow devices like EEPROM and all that stuff. It connects, so it can either connect to a single board or component via cable. And then we're going to see about the I2C implementation in Zephyr for I2C. Okay, first, as before we saw, we have to do the device get binding. So for the master, we are going to actually get the device, and we have to do device get binding to get the structure or the device for which we are going to carry out the operation. Once the device is obtained, we are going to configure I2C on this particular device. So we're going to say the config flags or anything that is to be set on this device using I2C configure. Once the I2C is configured, we have to write or read the data from it. That is done using I2C write. Now what happens, this is the I2C device and this is the buffer. Buffer, the first byte of buffer is going to hold the starting address from where it should write. That is, I2C write is going to write this data present in buffer on the device. Which device? The slave device with this address. Okay, this is the address of the slave. So first it is going to identify this address and then it is going to get to the address that is specified in first byte of this buffer. Once the address is reached, it is going to write all the data that's present inside this buffer for this much length. Suppose we have 30 byte of data that is to be written, then the length will be 30. So now 30 plus 1, because we have 1 byte of address also. So it's going to go to this and it's going to write that much of data into the buffer. That is I2C write. And then I2C read. I2C read, it is going to read the data. Just like I2C write, it is going to read the data from the buffer. Instead of writing to the data, the logic remains the same. Then we're going to see the sample that I2C sample that we used for our ultrasonic sensor. The sensor is a fast device when compared to the EEPROM. So as we get the distance measurements, we are going to write it to a buffer and then we will eventually write those data to the EEPROM. So we used I2C to communicate or to actually transfer data between the sensor device and the EEPROM. So data stored or retrieved from EEPROM using I2C write or read. So first what we have to do is we have a slave address for this EEPROM and we have defined this address, and this address will be used whenever we have to write any data. So first we are doing a device get binding for the master. Just like before, anything in Zephyr implementation will require a device binding if we to actually find out on which device we are going to perform the subsequent action. So similarly, we have to get the master device because you're going to write the data from master to slave. So once the I2C device is obtained, we're going to configure and set the mode to master, and we're going to set the speed also for this particular I2C device. Once it is configured, we're going to do the I2C write and read action on this particular device. So this is the data buffer. This is a data buffer, and for this much amount of this much length, we are going to write this data into this device with the slave address. Okay, this is I2C write, and once the data is written, we can actually read the data from the EEPROM using data buffer, the same thing as we discussed earlier. So that's what it is. I hope you enjoyed. I have also pasted a reference link which talks about, this is the actual documentation that's available for Zephyr project. I hope you liked the video. Thank you.